Alright, let's fix some memory leaks. Yeah. I don't even know how to debug this, to be honest. Probably reducing this to a minimal example that still leaks memory. So currently this is the source code. Can we simplify that? Let's say that we actually just want to print hi, and then we exit. Does that still leak memory? It doesn't. Okay, interesting. Interesting. So this really is an issue with, I don't even know, formatting ints, maybe? Let's say this is just 2. Like, what was it, 20? Is that still problematic? Yes. Okay, we can work with that, but that means we can basically remove this part, which was from the previous video, the previous session. Yeah, Fizzbuzz and the number guessing game, let's remove those for now as well, I think. Alright, so we want to print 20, and then we want to exit. That seems reasonable, first of all. Maybe let's, if we just format 20 without printing it, and then we exit. Does it still fail? Yes. Alright, so formatting 20. What does that actually do? I think in the int module, there's the format function. Let's actually copy that in here instead of importing that. So format int, no. Instead we'll use this function that we wrote ourselves. Int is negative, it's not, so this would be the false variant. And then this concatenates some strings apparently. Oh, that's not good. I think this depends on some other functions like dividing integers and probably format digit. Well, I don't even know if that's like public. So let's copy that over as well. Oh, that's horrible. But sure. Mod, do we import that? Yeah. Okay, let's test this out. Leaks memory. Alright. What if we try to print, try to format not 20 but 2 instead? Same thing. Yeah. Okay. What if? So let's see, int is less than 10. Alright, so this would just be an empty string. And then the 2 mod 10 would be like that. Okay, still leaking memory. What if we turn that into that? Is concatenating strings the issue, maybe? It is. Alright. That simplifies things a bit. So that really the problem is concatenating strings. I threw it out. This leaks memory. It does. Alright. Okay, I can deal with that. So where is that plus coming from? Here, plus of 2 strings. Oh, that's imported twice. That's not good. Anyways, in the string module, we do have this plus function that kind of concatenates the underlying arrays. Sure. And that requires concatenation of arrays, which is in the array module, concatenating these. And then that requires some other stuff like generate array. Okay, we do have that. Getting the length of arrays, yeah. Less than comparison. Yeah, we do have that. And array.get. And minus. Yeah. Alright. So this should compile, right? Alright. Cool. Pretty cool. Also, we can see that this gets smaller and smaller, you know, the binary. 4,488 bytes, and the oh, it's actually bigger. Well, meh. Okay. Let's maybe simplify stuff even further. Let's inline this into here, and maybe let's just call concat these bytes and these bytes, like so. And why not call that A and B, just for good measure, simplifying the code even further. Okay, that doesn't work. Because this is a function call of this. I think we need parentheses here, like so. Smaller, definitely smaller. All right, so let's do that directly in here, I guess. You know, let's just say A equals A. W of 8 bytes, and B equals B. W of 8 bytes, and then we generate an array, and that's it. I'm just generating the array and doing nothing with it. Still leaking memory. All right. Yeah, slowly. Let's beat the 4,000, yeah, and then we can look further. So here we're getting the length of A, which we know is just 1, actually. That's a bit simpler, right? And then the length of B, well, that's just 1 as well. So let's actually generate an array of length 2. Progress. Okay, and then for the index, we kind of capture these variables, which, I mean, I guess that's fine. Let's only capture 1 and see if that's still, you know, not even use B. All right. Oh yeah, that simplified things a lot, actually. Wow. I mean, B is not even not even used, so and here we're generating an array of length 2. Let's actually generate an array of, you know, integers, not not other arrays. So can I do, I don't know, b equals 5, and then I'll just replace this with b. This is still capturing something, this lambda, but it's a bit more complicated. Oh yeah, still crashing. Whoa, that simplified things a lot. Wow, so 1800. Problem is getting simpler and simpler. Alright, generate array of some integers, and then in here let's just turn that into this. Just always returning b. Still leaking memory. Alright. Do we even need to capture this? Or can we just have that in there as a constant? That still works. Crazy. Okay, so generating an array of length 2, that just contains the 5 2 times. Sure. Let's do that with the length of 1, maybe. Alright. And that leaks memory for some reason. That's not good. It is quite simple, you know, but yeah, generate array is a built-in function, so I think this, actually I can't simplify this any further. It's just not possible. Let's maybe look at the pudding, because that's the compiler stage with reference counting instructions. Oh, actually, you know what, that's first of all, disable this debug message. We need a tag size on this one. Let's remove that. Boom. And then let's print, hang on, let's execute the pudding compiler stage. Yeah. So we are running the main function with 5. We print the result. And then we kind of drop the result, I guess. Sure. Because in the conversion from, you know, whatever it was before to pudding, yogurt to pudding, and we kind of add dupe and drop instructions, these kind of reference counting instructions. And by, oh, hang on, that's useful, by actually executing that compiler stage, we then kind of double check that. In this run function, there are a lot of assertions that make sure that the reference counters, they make sense. And here we ensure that everything is freed, so this is like a very strict execution of the program. Which means that if there are any errors in there, they hopefully show up here. And if they don't, then we know that the pudding makes sense, and that the error is introduced somewhere later in the compiler pipeline. Okay, that actually worked. That's a bit surprising. Okay, so oh, there's the pudding. There's actually not a lot of code. That's cool. I like that. So we have this main function. It drops the argument. It creates a 1. It creates an empty struct. Box is that. That's the closure of the lambda, of this lambda, for creating the arguments. Boom, the lambda does this. When it's called, it kind of takes ownership of the closure and the actual argument, the index. So here it kind of drops the index. We don't need that. We unwrap the closure, and yeah, we drop that. Calling unbox consumes this closure pointer and returns us the empty struct there. Makes sense. Then we drop that empty struct, and then we create a 5 and we return that. Makes sense. So we're basically dropping all of this, this int and the closure pointer here. Alright, so in the main function, we've kind of created this closure, we've created the lambda, and then we call generate array built-in function with the int, the length, and the lambda for generating integers. So we drop the resulting array, and we create an empty struct so that we can then construct the exit variant of the task type and return that. Perfectly fine. Like, that seems super reasonable. And you can see that in the end, all of the ref counts, they are 0. Yeah. Here we're still running one expression, I guess. And then we're dropping, we're dropping that thing here, which also drops this struct. Yeah, kind of explicitly doing that here because you're the main function, it returns exit, and the exit enum variant containing an empty struct, but it kind of gives us ownership of that as it returns. So in the waffle we have the text size is that a remnant from before. Let's remove that. All right. Cool. So the pesto works, which means I'm going to not run that actually. All right. What else? We could run the waffle, just checking that that makes sense. Yeah, let's print the optimized waffle. I think that's a bit more fun than just printing the original one. So the waffle should be a completely different sort of beast, yeah, with all the dupe and drop functions actually being written out. All right, so here dropping a box of an empty struct defines a local, while the parameter stores that in a local variable. Then it does what? It loads that local, because that's a pointer, you know, it's a box, to actually a reference count and then a struct. So all heap allocated things have a reference count. We load that, and then we subtract 1 from that to decrement the reference count. So that's this right here is the new reference count actually. We store that into the heap allocation, and then we switch by comparing that new reference count to 0 in a complicated way. And if it is, what is this? If it's equal, yeah. If it's less or greater, we don't do anything. If it's equal, if the reference count is 0, then we actually, we take, hang on. We are loading 0 bytes. Do we really need to do that? I think we can optimize that away by kind of adding 8 to that pointer, skipping the reference count, loading the payload of size, so the actual heap allocation there, and not doing anything with that as far as I can see. And then freeing the original pointer of size 8. Just the reference count, because it doesn't really contain any data. Then generate array of int. Boom, we have some parameters. 32, that's like 4 pointers of ints or something. So I think this is the length, and then the lambda. And the lambda consists of a function pointer, a pointer to freeing the closure, and a pointer to the closure itself. Yeah, so first we kind of get the member at offset 24. I believe that's the length of the array, probably. Yeah, we want to generate an array of ints, so we multiply that with 8 to get the number of bytes that we need. We add 16 because buffers store the reference count and the length in there, so we need 16 extra bytes for that. Then we allocate memory for that. Boom. For our buffer that stores the data. And then in that buffer we store a 1, that's the reference count, plus in that buffer plus 8 we store the length of the array that we want to generate, so 1 in our case. And then we call init array of int using the lambda and the buffer, and probably the cursor or something like that, and then the length. All right. And then in the end we call, we kind of drop the lambda. So running the waffle, I think let's do that as well. Just to see what's going on there. Because I am kind of tired, so maybe I won't continue too long today. Oh, that's interesting. So running the waffle actually fails. Well, that's unfortunate. That sounds like a panic thing. Solve M92. What's going on there? Oh, we do as a string. That's, oh, that can't be good. Waffle.run. That is, I think that kind of reinterprets memory and stuff in a way that we don't want. So let's not do that. And yeah, that's just a slice of bytes, so what? We can make that work. Right, so this is what the function returns, and you can see that this is the exit task plus padding. I think this is like AA in hexadecimal, which is our padding. Okay. I'm not sure what exactly is going on there. Okay, so running the waffle works, but we don't check memory leaks, really. So, yeah. Well. Yeah, I see, we just have the visible bytes and that's it. We don't check leaks. Well, that's unfortunate. Let's see how this today we start at the main function and see how kind of ownership propagates through these functions, because it should be manageable to track, I think. We are given a parameter, okay, we don't care about that, that's just an int. We allocate 8 bytes. We store a 1 in there, a reference count. Then we call, well, let's start in the center here. We build a lambda that consists of a function pointer to the actual lambda body. It consists of a closure, which is this kind of thing that only consists of the reference count we've just created. And it creates a function for dropping the closure. Okay. And then we put that in a 1. Fair enough. Plus we call generate array of, array of int. Generate array of int, and we've looked at that before. Generate array of int. That was up here somewhere. Yeah. That would first of all allocate. Hang on, let's look further on the main function actually. So in here this generate array function is supposed to take ownership of this lambda and free that lambda for us. That's so even though we allocate memory up here, because the reference count is 1 and we pass ownership of that into generate array should take care of freeing that lambda after it's done, creating the array. And then drop array should kind of drop the array. So after this, there should no longer be any memory. So there are basically a couple of things we can check now. I want to look into generate array and check how that handles the lambda here, especially this closure here. That's the critical part. This heap allocated thing that only contains a reference count of 1. What happens with that? And then if that's looking fine, then we can see what does it actually return. Does it return a heap allocated array, and does drop that correctly? So does it tell us the size of the allocation? Memory address something leaked. In here, malloc of size 8. Oh no, that's the alignment, never mind. Not really. Okay, fair. Hang on, we were just looking at generate array. Okay, we can do that. This is doable. We have the parameters. All right. We looked at that before. We allocate memory of 16 plus the length of the array times 8. We store 1, and there's the reference count. We store the length, and there's the length at pointer plus 8. We initialize the array. We call init array. This receives the lambda, but it's not, it isn't responsible for freeing the lambda, so that's fine. So hang on, currently the reference count of the lambda is 1, and we want the reference count here to remain at 1, so that we can later on drop that. Okay, what else? We have, this was this, the buffer basically that we allocated, a cursor and the length. Okay, but shouldn't affect the reference counts of these. Then we do a drop of the lambda. And then we create an aggregate of the array, the pointer to the buffer basically. And then this is the start and this is the length. Okay, that makes sense. Like this, I can see this makes sense if this works correctly and this works correctly. So let's look at init array. This should not take ownership really of these. So it should just, given an existing buffer, an existing lambda, just fill it up with data. And that is down here, init array of ints. Okay. So what do? We quite a lot of stuff. So we don't return anything, an empty aggregate. Fair enough. Because this function is its only point is to have side effects. So we take this. I see, we subtract at offset 32. Let's kind of peek up here what happens. What exactly is that? We have 24 bytes of the lambda, followed by a single pointer to the buffer, followed by the current cursor, I believe, and then the length. So down here at offset 32, that would be about 16 bytes. I see. So that's the cursor and then the length. And the sub then subtracts that. So cursor minus length. Sure. compare that to 0. Now if it's cursor minus length, if the cursor is this is the equals case. If the cursor is equal to the length, I believe, we don't do anything. Okay, that's actually fair. Yeah, this is the greater case. If the cursor is greater than the length of the list, not possible. Yeah, we don't do anything. Fair enough. But if the cursor is less than, less than the length, then we do some stuff. Makes sense. Then we want to fill that item at that cursor position. All right, so we take the lambda, and we take the closure. We do that here as well. We load 8 bytes there. That gives us the reference count. We add 1, and then we store that back there. So this increments the reference count of the closure of the lambda. Makes sense. Because when we call the lambda will consume the closure. So in order to just being able to call the lambda, we need to increment the reference count of the closure before. Yeah, then we actually call the closure. So this, what's going on here? I think there's like some weird formatting issue. Should be in a new line somewhere there. But we do a call indirect of some member. I think call indirect has, I think this should be a new line here. And this aggregate is on the same level as this one, I think. So this is kind of the pointer that we want to call, and these are the arguments that we're giving to this indirect call. All right, so we have this, oh yeah, that makes sense. This is the lambda. And then in that lambda at offset 0, that's the function pointer to the lambda body. And we call that lambda with an aggregate. The index, like the current cursor basically, and then the closure. And the closure is going to be this is the lambda, and then the member at offset 8 is the closure pointer. All right, so we call that lambda, which kind of undoes this basically. It decrements the reference count of the closure because it consumes the closure. And it returns us something. It returns us the int that it wants to fill into that array position. Yeah. So far, that makes sense. Then we now have the thing that we want to store into the array. And I think next we do that, yeah, we store that int, that 5 in our case. We've called this lambda, it returned 5. Now we want to store that 5 into the array. So store that 5, the result of that indirect call of that lambda, into the array. So this is, I was adding some stuff. It's adding the, this is the lambda what was this? This was the x24. Should write that down somewhere, I think. Like, hang on, the first 24 bytes, they were the lambda. Oh, I see. Then came the buffer. So this is just the pointer to the buffer. I see. We skipped the first 16 bytes because that's the reference count and the length of the buffer. So this is basically where the items begin. And then to that we add even more. We add kind of the offset of the item that we want. And that's the, you know, the cursor times 8. All right, yeah, that makes sense. And then we call ourselves recursively with, well, yeah, with the lambda and the buffer pointer. Makes sense. Then, what is this? Oh, this is the cursor plus 1. Fair enough. Yeah, cursor plus 1. And then this is the the length, right? Yeah. Okay, so we call ourselves recursive. Fair enough. Whew. And then, after that is done, we basically return to this generate array function, which was up here, generate array. Beautiful. So we've initialized the array. Yeah, the reference count of the array wasn't changed. The reference count of the lambda wasn't changed. Well, it was incremented before every call, so it kind of balances out. And then down here we drop the lambda. Let's see how that works out. We drop the lambda. So what we do is we load the, like, this is the closure pointer, basically. Pointer to the lambda's closure. We load the 8 bytes there, that's the reference count. We add, oh, hang on, we subtract 1. That's going to be the new reference count. We store the new reference count into that same closure. And then we switch on the new reference count. Hang on. Yeah, we switch on the new reference count, fair enough. And then, what then? We if it's equal to 0, you know, if it's something else, that's fine. If the reference count is 0, though, we want to free that closure, which means we're going to get the member offset 16. That was the function pointer for freeing the closure, and we're going to call that with the closure pointer. Yeah, that's fine. And let's also have a look into the main function. Yeah, and here that's going to be a function pointer to the drop function of a box of a struct. And we looked at that before, I think, and that seemed reasonable, where, yeah, we would just load the reference count, subtract 1, that's the new reference count, and then we, oh, hang on, one thing, we drop closure. I think that's actually not correct. I think I found it. Yeah, we here we take. Okay, so hear me out. A lambda consists of a function pointer to the lambda body. It consists of a closure pointer, and it consists of a function for dropping the closure, not freeing it, but dropping it. That's the thing that changed, I believe. Previously, I had in here a function for freeing the closure. Now it's just a function for dropping it. And in here, dropping a lambda, that actually, already loads the function pointer, loads the closure reference count, subtracts 1 from that. So our reference count of 1, we calculate 0, we store that 0 back into memory, we compare that to 0, we see, oh, that's actually 0, let's drop that. So then we call the drop function with that closure pointer, which will drop this box right here, which will then load the reference count of that same closure pointer, which will at this point be 0. It will subtract 1 from that, that's minus 1. Ooh. It's going to store the reference count of minus 1 in there. That's, ooh, no, not what we want to do. We compare that to 0, we say, oh, it's not 0, so we don't do anything. I see. So actually, the problem is in the pudding to waffle conversion. Pudding, hang on, no, something to waffle. Pesto to waffle? Pudding to pesto, okay, somewhere in here. I think in here, dupe drop free stuff. Yeah, compile dupe fun, okay, dupe is not the problem, compile drop fun. That's the difficult part. Yeah, for the lambda.
Exactly.
Yeah, here we decrement the reference count of the closure pointer. Which is actually fair. Like, there were basically two ways we could deal with this. First, we could change it so that dropping a lambda doesn't just doesn't directly decrement the reference count, but instead it calls the drop function, like it calls this function pointer. However, if we have multiple lambdas with different closures, we can treat them the same way. We don't need them, like an indirect call in there. We can just decrement the reference count of this. That should be totally fine. The problem is really just freeing the value. So I think what we rather want is, we have compile drop fun. Now we don't have some sort of compile free fun or something. Instead, we always have, like these free things in here directly. Yeah, Okay, I see that. I mean, the lambda's closure is basically a box. So that's kind of take that as a baseline, put that down here. Oh no, hang on. When creating a lambda, yeah. Here the free function pointer is not just the drop function. No. This should be something else. Either that. You know what? I'm gonna go the easy way for now. Yeah, I'm just gonna say if you drop a lambda, I mean, this is called free, you know, so. Yeah, let's compile a separate function for that, sure. Hang on, compile dupe fun, compile drop fun, compile drop buffer fun, sure. Compile drop buffer items fun. Alright, and we don't need to deal with the reference count. We know that the reference count is 0. So we can just do that. We do build it up call. Nope. We load the content of that box. Similar, by the way, to what we do in the drop for the box in here. We just drop the inner, we free the original box, and that's it. Yeah, makes sense. And then when compiling a lambda, instead compile this, you know, box content free fun. Actually, let's compile closure. I don't know. That's yeah. The type of the closure is a box. So we do kind box unwrap that gives us the inner type, and then we can use that here. All right. No more memory leaks. Clean, nothing like this. Oh, that's really cool. I like that. Also, like, let's adjust the waffle printing because that will call indirect. Yeah, there needs to be a new line between these. That's what I've figured out. Yeah, pretty cool. All right, and then in here, let's disable the printing, I guess. False, false, all right. Yeah, yeah, I guess that's fine. Sure. Cool, very, very cool. Yeah, let's run that again just to make sure that there is no like debug output. But otherwise, I think we're fine to commit this. Fix memory leaks. Fantastic. Cool, I like that. And that's it for this video. And see you in the next one. Bye.